Welcome to our today's reading group. So in our today's reading group, I will introduce two papers related to the logical rule learning. And then the first paper is RNNLogic. So this paper trying to learn logical rule for reasoning on knowledge graph. And the second paper is R5, the rule discovery with reinforced and the recurrent relational reasoning. And then we will begin our today's presentation by introduce the first paper on RNNLogic. So this paper is published in ICLR 2021. This paper trying to target at the problem learning logical rule for knowledge graph reasoning. So as shown in the slides, we can see that given the knowledge graph, actually we can learn the logical rule which trying to describe the underlying pattern of the data in order to explain this knowledge graph. And then by plugging this logical rule back into this knowledge graph, we can infer some unobserved triple, and then in order to predict the missing knowledge. And because logical rule is easy to understand by human being, so it shows good interpretability. And then also even though we're trying to learn logical rule from training data set and apply this logical rule to another unrelated knowledge graph, this logical rule can still be well generalized to the unseen entities. So this the logical rule is also have very good generalizability. That is the reason why this paper trying to learn logical rule and then leverage the learn rule for knowledge graph reasoning. First of all, we would like to formalize the logical rule learning problem in the probabilistic way. So the idea here is that given a query, here a query is the example query is we have the head entity Alan Turing, and then we would like to know what is his nationality. And then the goal here is to infer the tail entity, which is the nationality of the Alan Turing. And then in order to achieve this goal, the idea here is that we would like to first learn a rule generator. And then this rule generator will generate a set of logical rules. And then by plug in this learn rule into the background knowledge graph, and then we would like to train a predictor to predict the answer of the target query. So that is like the basic pipeline of rule learning joined with knowledge graph reasoning. There are several related work trying to solve the same problem. And then the first direction of the related work is based on the inductive logic programming. So the idea of the inductive logic programming focuses on learning a good predictor. So here the basic idea is that it will trying to search over the whole knowledge graph and then enumerate relational path between query entity and the answer entity as candidate logical rule. And then it will trying to assign a scalar weight to each candidate rule in order to make the prediction. Because the inductive logic programming usually have a very simple generator. So here the generator can just simple as enumerate all the appear relational path in knowledge graph. So essentially, this kind of method will suffer from a huge searching space of logical rule. And then that will cause some challenge for the running time of this kind of approach.
And can I ask a question here?
Yeah, sure.
Do they assume all the logic rules are independent or not?
Yes, they assume.
But they are not independent, right?
Right, they are not independent, but most of the work in this area assume that the logical rules are independent with each other. Yeah.
Okay.
So the second direction for logical rule learning is the reinforcement learning based approach. This approach different from previous approach. This approach focuses on learning a good generator. So the general idea of the reinforcement learning is to train a pathfinding agent, and then this pathfinding agent will search for reasoning path in knowledge graph in order to answer the query. And then because it trying to learn a strong generator, so it could have more efficient search compared with the previous method. However, training and a good pathfinder agent is a challenging task because the reward signal are usually sparse in knowledge graph. This kind of method usually suffer from the training for the pathfinding agent. In summary, we can observe that for the inductive logic programming, they usually have a very strong reasoning predictor, and then for the reinforcement learning, they usually propose a very strong rule generator. And then in this paper, the author proposed to jointly train both rule generator and reasoning predictor in order to better learn rule as well as reasoning, conduct reasoning over the knowledge graph. Next, we will introduce the detail of the framework of the RNNLogic. So we will begin the introduction of the RN, as we just introduced. The RNNLogic mainly include two components. The first component is the rule generator, and then the second component is the reasoning predictor. And then we will introduce the whole framework by first introduce the rule generator. So the idea for the rule generator is that given a query queue, the rule generator trying to generate a set of logical rule in order to answer the query. And then here we just like present example in the slides. We can see that so here our goal is trying to answer the query. What is the nationality? So what is the nationality of X? And then the rule generator will trying to generate a set of rule which can leading to the answer of the head relation nationality. And then we can see that because in this paper, the goal is trying to generate the train-like rules. So here, this, like as shown in the slides, this is an example of Cheng-like rules. And then we can observe that the body of the Cheng-like rules is usually a path in the knowledge graph. So given a concrete path in the knowledge graph, by eliminate all entities from this path, we can obtain the we can obtain a sequence of relation in the body. So the idea of this rule generator is that it will trying to convert a logical rule into a sequence of relations. And then this sequence of relation will be the first relation in this sequence will be the head relation, and then it will follow by the first relation in the body, and then the second relation in the body, and then finally it will trying to add the Rn in order to indicate that this is the end of the relation sequence. And then given such sequence of relations, it's trying to leverage RN model to calculate the rule probability. And then that will be the basic idea of the rule generator proposed by the RNNLogic. And then given such rule generator, we can learn a set of logical rules in order to predict the query. And then the next question will be that we would like to leverage this rule in order to do the reasoning part. And then the idea here is that we would like to use the stochastic logic programming to define the reasoning predictors. And then we will still use another example to show the basic idea. So for example, we have R1 and R2, and this we assume that these two rules are generated by the rule generator. And then the reasoning predictor trying to leverage these two logical rules in order to answer the query, what is the nationality of the Bob? And then here is the background knowledge graph. And then the idea of the reasoning predictor is that we're trying to plug in the generated rule back into this knowledge graph. And then we will achieve some grounding rule following this learn rule by grounding the entity Bob into the logical rule. And then we can see that both R1 and R2 can lead to the same entity friends. So the score of the entity friends to be the correct answer to this query will be calculated as the score of the relation, the score of the logical rule 1 plus the score of the logical rule 2. So in this way, we can assign the score to all possible answer, and then by ranking all these possible answer, we can find out the final solution for this query. So that is like the basic idea of the reasoning predictor. And then after introduce like the basic idea of the rule generator and the reasoning predictor, our next question will be how to optimize this two part in order to jointly learn both components. So here, the idea is that at each training iteration. So first of all, we have these two components, rule generator and the reasoning predictor. And then at each training iteration, we're trying to first update the reasoning predictor according to the rule generated by the generator. And then this reasoning predictor will return the subset of high quality rule as a feedback to the rule generator. And then the rule generator will optimize itself based on these high quality rules in order to achieve the optimization goal. And then this process will be complete by leverage the EM algorithm. So here, so first of all, the EM, we will introduce this like EM algorithm by first introduce the E-step. So in the E-step, the idea here is that we would like to optimize the reasoning predictor. So this reasoning predictor will take the take the generated rule by the rule generator as the input, and then it will trying to select the top K high quality rule as the most promising rule, and then it will trying to return this most promising rule back to the rule generator in order to guide the learning of the rule generator. So the idea here is that we have already introduced before that by plug in the logical, in this like framework, each logical rule will be associated with a confidence score. And then by plug in this logical rule back into the knowledge graph and grounding based on the query entity, we can calculate the score of the candidate answer using this by added this confidence score together, the confidence score of rule together. So
how is the confidence score established?
Oh, so actually for this reasoning predictor, the idea of this reasoning predictor is that it will take a set of logical rules as the input, and then it will trying to learn confidence score A for each of these logical rules. And this confidence score A is trying to measure the plausibility of the rules. And then by leverage this confidence rule in calculating infer the answer for the given query and optimize this inferred query by compare it with the ground truth answer, we could optimize like the confidence score of this the set of logical rules. Is this part clear?
Still not quite clear how to learn that confidence score.
All right. So here, for this reasoning predictor, we're trying to associate a parameter with each logical rule. And then this parameter is just a scalar weight.
So each rule has a scalar weight as the confidence.
Right.
So that is A here,
then,
or A is something different?
A is the confidence.
A is
sorry. Here,
no.
A is the query answer.
Oh, A is the answer. A is not the confidence. Oh, okay.
Right.
Is that confidence score like QZ given all the existing?
I think it's
data?
W. The confidence score here is W.
Confidence is W.
Right. So it is the parameter of the reasoning predictor.
Is that parameter or something related to each step? We want to calculate the conditional distribution of for each rule, which did not see here.
Yes.
So
it is conditioning to the query. So for each different query, we're trying to learn the parameter W.
Or the probability, conditional probability for that particular rule.
Right.
So that's corresponding to the each step.
Right.
I see.
So for the each step, how do you exactly, I think you mentioned the RNN. Do you turn the RNN score and make it a probability?
Right. So here, as we show in the rule generator, we will leverage our RNN model in order to calculate the rule probability. And then by sample the rule based on this probability, we will have a set of logical rule. And then we will fit this set of logical rule to the reasoning predictor. And then now the goal of the reasoning predictor is trying to maximize the probability of the ground truth tail answer to be inferred based on this set of logical rules.
Then in this example, you have this score friends, right, equals the 5 R1 plus the 5 of R2. What are those two? I mean, two functions.
This function will be so the detailed idea of like how to calculate this function is that it will trying to leverage the knowledge graph embedding, and then it will trying to compare. So following this like R1 and then the R2, it will achieve like the tail entity. And then by comparing the similarity of the ideal tail entity and entity friends, we will use this similarity to measure this W.
Is that can only be positive number?
Yes, the W can only be the positive number. So we won't consider any rule which will have lead to the negative result of the infer.
Well, I have a question. Like for example, if you for Bob, right? So if you have a relation saying Bob right now is born in Paris, right? Paris is Bob for France. Let's say you have another one like Bob, let's say visited another. You have the example, right? Another country, Canada, right? He visited Canada, right? So, so all of them you add up, or I mean, let's.
So
here,
to me,
like you only add up those two, like relate to France, right? But but for all the other country, I think should have some negative contribution to that, right?
Oh, the idea here is that so for example, the goal here is to find the answer for the query Bob and what is the nationality of the Bob, and then the ground truth essentially is given in the knowledge graph. So for example, this ground truth will be France. And then now the goal of the reasoning predictor is that we're trying to plug in this knowledge graph into this, we're trying to plug in this logical rule into the knowledge graph. And then by adding the confidence value of the ground logical rule together, we're trying to make sure that the friends will always have like a very high score as the tail entity of this query.
Yeah, you mean have the highest score, or because there's another country like Canada, right?
Right.
Could also have very high score. Right.
Right, but in that case, we won't take it into the consideration when we calculate it. So we only care that as long as we ensure France has very high score, that is. Oh, sorry, I think I make mistakes here. Yes, so finally, this score will be normalized over all possible entities. So the idea here is that we will use, so the probability A equal to the friends is essentially the score of the friends divided by the sum of the score of all possible entities.
Right. But
Yeah.
But if France is the ground truth, right? Then
Right.
you want the score for France is higher than the score for other country, right?
Right.
So in this case, let's see if you have another one, like I mean, the visited may not be that strong thing. So you have another rule like lived in, right?
Right.
Right. Then that's another strong indicator, right? And
Right.
then maybe Bob lives in US, for example, right?
Right.
Then so my point is that when there's a conflicting evidence, right? Well, he was born in France, but he now lives in US, right? So which nationality he has? So when there's like two strong conflicting evidence, I just wonder like how this this model going to
Right. That
evaluate
is,
that.
yeah, that is a very good question. So actually, this model can only leverage the positive signal from this model. It cannot like leverage, for example, the complete result in order to address the parameter of this model. So for example, friends should be, for example, we have example, and then we have a knowledge graph, and then by leverage this knowledge graph, we may both infer Bob has a very high probability to be a male, and at the same time, Bob will have a very high probability to be a female. And then by following our common sense, that should be a complete example. And then the model should have a problem if we infer both female and the male of the Bob can both be male and a female. And then at that case, this model won't do anything in order to address that situation. Okay. So yeah.
Yeah, I think that's a very good point.
Yes.
For example, if there are like 100 paths from Bob to France, each of them is associated with very low score, meaning that actually it's kind of negative example, but adding all those 100 small values together,
yeah,
potentially it could be big.
Yeah.
Right.
Actually, like, I mean, the way they treat it, like they just added those scores together, right? Those are not probability.
Right.
For probability, you can't just add them together.
Right.
Right. So right now they just first utilize the grounded path to calculate score, and then turn score into probability. And according to the counter example we just discussed, then probably we should first turn it into probability and then calculate the collective probability. Right.
Right.
Yeah.
But as we just discussed before, so logical rule itself will independent with each other, but usually all the model trying to model them as independent evidence. So this collective probability might be, if we're trying to following like the underlying relation among the logical rule strictly, I think this collective probability would be hard to compute.
Another question I have is that right now in this particular example, right, each path is kind of a separate path, right? So
Right.
there's no sharing of edges. But in reality, especially you have this multi-hop relation, right?
Right.
And that there may be some part actually there's a two paths have a like sharing edges.
Right. Yes, for that part.
Do they still just add up the score?
Yeah, they just add up the score. So according to my knowledge, like the simple addition is like the widely accepted way in order to conduct the reasoning based on the rules. Yeah. So that might be a big problem for current research.
Right. Yeah, I also have some other questions for the space of the rules here.
Yes.
Do they enumerate all the possible rules under some length constraint?
Yes.
So for example, if it's like length 2, then it's like the size of relation
Yes,
times
we have to first specify the length. So we only like for example, if we limit the length as 3, then we only search over the rule space with max length of 3.
Okay, so if it's a large graph with 400 relations, then it's going to be 400 cubic, right?
Right.
Okay. And next question is.
But I just want to mention another thing, because we leverage the RN. So we don't need to enumerate all possible combination, because like at each step using if we use RN at each step, we essentially will trying to choose what would be the best next step, right?
So do you say that we actually need to do like random work on the large graph, so then we can leverage the sparsity of the graph?
No. So the idea of this work is that we first have a RN, and then at the first step, this RN might be have very low capability. And then we may like generate the next relation by just randomly pick something in this relational space. But by fitting these rules into the reasoning predictor, this reasoning predictor trying to find out the most useful path in order to lead to the ideal tail entity. So and then this like reasoning predictor will return these high quality rules based on this prediction result to this generator. And then the generator will trying to retrain this RN based on these high quality rules. So you can just regarding that after I select some high quality rule by the reasoning predictor, and then we just return the sequence of relation to this RN, and then you ask this RN to learn to fit over this
I think
example.
what you're saying here is like RN will assign different probabilities for each candidate in that rule space. But the potential of the rule space is R squared, R cubic, given the length is 3.
Right.
The poise is better because it's sparse graph. So if you consider the valid length 3 path, it's not all the possible combination. So I mean, the candidate space probably is still like much smaller than R cubic. And of course, it will assign very skewed distribution to them.
Right.
Okay. Then next question is for the W. For the W, to me, it seems like it is like conditional probability over all the rules in the rule space.
Right.
So then W should be a vector, right? It's just very confused about the notation of the W, because to me it's just conditional probability over all the Z.
Right. And because here it is like conditioning on Z, so I guess it's just trying to show them this
way. Z can take a value like R1, R2, R3.
Yeah.
Case. So then for the score.
Oh, sorry. The query is Q, and the Z is a set of rules.
And the W is the probability.
The W
over
will
rules.
conditioning on the query. Yeah.
Condition on the query on Z, is that right?
Yeah. Condition on query on Z. Yeah.
You said Z is a set of, is the entire set of rules, or is a selected set?
The selected set.
So they use some threshold.
So this Z is generated by the rule generator.
Z is and R1 and R2 just part of Z, is that right?
Right.
Okay.
So when I say generate a rule, for example, generate a sentence is just one possibility. It's like, because every time we just select the most promising relation.
Right.
Then there must be some like threshold, for example, the top K for each step. Otherwise, it's just a one sequence is going to be generated.
Right. It will trying to so the goal of the reasoning predictor is trying to select the top K rule from the generated rule, and then return this top K rule back to the generator.
Because the RNN is like every time it's just to predict the next most promising relations. It's like every step they choose top K, so then they're going to generate like K to the power 3.
Right.
And then they are going to select another top K.
Right.
Okay.
So the idea here is that, so first of all, because the rule generator, there's no signal to guide the learning of the rule generator. So it is highly possible for this rule generator just like randomly select some relation to build this candidate rule. And then this reasoning predictor will trying to select the most promising rule based on the prediction ability of the rule. And then it will return this this top K rule back to this RN. And then the RN will trying to fit itself based on this top K rule. So so at this point, this rule generator will can receive the signal or the guidance from the data. And then this RN model can be improved based on this return high quality rules. And then after that, so we will again use this RN to predict, for example, the K to the power of 3 rule. And then we will fit this rule to the predictor. And then this predictor will again select, for example, top K rule, and then return to this RNN model. Yeah.
For the score function, that W is the vector. So is it like a weighted combination of different rules involved?
Yes. So so the idea here is that this W is just trying to so for example, we just forget about like the rule generator part. We only focus on the reasoning part. And then the idea here is that we are given a set of rules, and then we're trying to associate with each rule with confidence score W. And then now our goal here is just trying to learn this W. And then in order to maximize the probability of the ground truth result to be achieved.
So W is not the Q in the previous slide?
Sorry?
So I thought W is the Q, conditional probability in the previous
yes,
slide.
Yes.
So then W is already down in the E step according to that conditional probability, right?
Right.
And here, is it just the weighted combination of the score obtained for R1 and the score obtained for R2, and the weight is determined by W1, W2, which is the probability calculated based on the Q function in the previous slide?
Yes.
Okay, then I think it's better to do some expectation over W of the two score, right? This size sub W is kind of misleading because for R1, we just need this W1, right? R2
Yes.
is W2. Okay.
Yes.
Okay, so I have another question about grounding. Is grounding a big concern here? Like,
yeah.
Efficiency-wise, is it a big problem?
Because we focus on the train-like rule, so I don't think efficient-wise will be a big problem. Although RNNLogic have very big problem, have very big efficiency problem, but I don't think the bottleneck is over the grounding.
Then what is the bottleneck in terms of efficiency?
I thought the bottleneck might be it require many iteration in order to learn a rule.
Or is it because it has to calculate that answer distribution vector, and the potential answer should be every possible entity?
Yes.
Is that
Yes, I agree.
That's going to be a very long dimensional vector.
Right. But if we trying to grounding, like if we only require the grounding to happen for one time, so I think the efficiency is acceptable. But here we will require this like every term. So
yeah, every time because our selected rule will be different.
Yes.
So somehow we have to do some regrounding.
Yes. But if this grounding only happen one time, so I think the efficiency should be acceptable.
Okay. Yeah, I don't have any questions.
Okay, so let's like So I think we have just already discussed like the process of this optimization process. So in summary, I will just like summarize this EM process again. So the idea here is that for the E step, we will draw a set of rule for each data instance or the query here, and then we will let the reasoning predictor to predict the ground truth answer for the query. And then in this process, the E step just trying to learn the weight associated with all the rule. In order to identify the set of K high quality rule from all the generated rule in order to maximize the probability for the ground truth result to be achieved. And then after that, it will return this high quality rule back to the rule generator, and then this high quality generated rule will feed into this RN model, and then in order to update the rule generator in order to maximize the likelihood of this high quality rule selected by the reasoning predictor. And then that is like the basic idea of the RNNLogic. And then the next part will be the experiment result of the RNNLogic. So RNNLogic just compare against some existing method, including the knowledge graph embedding method, as well as the rule learning method. And then this RN, so we can observe that because like the RNNLogic will still trying to plug in the logical rule back into the knowledge graph in order to make the prediction. So it is not like purely designed for the knowledge graph completion task like the KG embedding method. So the RNNLogic cannot like perform better than the knowledge graph embedding method on the free-base data set, but it have better performance on the VernNet data set. And then the author also compare RNNLogic with the baseline over the kinship and the UMLS. And then these two data set is relatively smaller compared to the free-base and the VernNet data set. And then the RNNLogic like perform better than the embedding method over these two data sets. And then the reason is that so the kinship data set and the UMLS data set is like related to some family relationship. And then this kind of data set have very strong like rule related pattern. So by leverage logical rule to conduct the knowledge graph inference, it will achieve better result compared to the embedding model. So that is like the experiment results of the RNNLogic. So next we will introduce, and then the author also present some example learn rule by the RNNLogic as shown here. And most of them are very reasonable. So next we will present another paper, R5 rule discovery with reinforced and recurrent relational reasoning. This paper is submitted to the ICLR 2020 to 2022. And then the motivation of this paper is that essentially a long haul rule can be decomposed into short haul rule. We just give an example as shown here. So for example, we have like a rule body, mother X Z1 and the sister Z1 Z2 and the father Z2 Y, and then by combine this the first two predicates in this rule body, we can infer that X essentially is mother of Z2. And then by combining the result, the conclusion of the first two predicate with the third predicate, we can infer that the final rule head should be the grandma XZ2, sorry, here, should be the grandma XY. And then the motivate by such kind of observation, we could leverage only short haul rule in order to conduct the more complex knowledge graph inference, which can only be conducted using the long haul rule. So there is like an example. So for example, we have a training graph 1. And then based on the data in training graph 1, we can infer the rule mother XZ and the sister ZY can infer mother XY. And then by observe the second training graph 2, we can infer the logical rule mother XZ and the father ZY can be used to infer the grandma XY. And then now we're trying to apply this logical rule to conduct the inference in this inductive relation prediction task. And then we can observe that if our goal is trying to infer the relation among the Mary and the Ann, essentially we will require the rule mother XZ1 and the sister Z1, Z2 and the father Z2Y in order to make the prediction, which is this path. But none of, so actually based on the training graph 1 and 2, we couldn't infer such long rule. But by applying these two short rule recursively, essentially we can still achieve the same goal by applying this long rule, by only applying these long rules. So motivated by these examples, the idea of this paper is just trying to maintain the rule memory model in order to record the short haul rule. So in order to build such rule memory model, it just trying to, this rule memory model is designed to store the item in form of Ri and Rj can be used to infer Rk. And then it essentially can be regarded as a table, and then this Ri and Rj will serve as the key and the Rk will serve as the value. And then by only store the rule with length of 2, and then the recurrently apply the the rule of length of 2, R5 can infer the result, which can which can only be inferred by the long rule. So that is like the basic idea of this paper. And then so next we will trying to introduce the detailed framework of this paper. So this, first of all, this paper, the goal of this paper is still trying to predict the relation between two entities in the graph by leverage the learn rule. And then the method is we will try to recurrently apply learn rule to merge a relation pair in the path to form a compound relation until it outputs a final relation between two query nodes. So here is like the framework, the overview of the framework of R5 framework. And then we can observe that this R5 framework take a knowledge graph as the input, and then its goal is to output the relation between two query entity based on the extracted rule. And then the idea here is that it will first transform a relation graph into a set of paths connecting the query node. And then after that, so this is like the first step. And then after that, it will recurrently apply the learn rule in order to merge a relational path until the final relation only include a single relation. So we just take this picture as an example. For example, our goal is to infer the relation between X and Y, and then there's multiple paths connecting X and Y. And then we just list all these possible paths here. And then for example, following the short rule, R1 and R2 can together infer R3. Now we can reduce this long path into a shorter path by replace R1, R2 with R3. And then by doing this kind of thing, by recursively conduct this kind of process again and again, finally, we will achieve the single relation to represent the whole relational path. And then this single relation should be the target relation we observed. So that is like the basic idea of this framework. And then after we give the overview idea of the framework, next we will trying to introduce the detail of the framework. As we just introduced, the first part of this framework is the path sampling. So given two entities from the graph, we will first randomly sample max L path connecting these two entities. And then based on this L path, we will construct a set of sequence, and then this sequence will only consist of the relation in the path, just as shown here. So here is like a example path, and then by extracting this relation in the path, we obtained this sequence of relations. And then next we will, given such like a sampling path, next we will trying to modeling the reasoning as a sequence decision making. So the idea here is that we will like to train a reasoning agent based on the policy value network combined with the Monte Carlo tree search to recurrently reason over the extracted relational path. So the policy value network will take the current state as the input, and then it will output the action probability distribution and the state value. We will introduce what is the action space and the state value in the following slides. So first of all, we would like to introduce what will be the action space for this for the reinforcement learning part. So here, the action space will be the relation pair, and then this relational pair just indicates two relation in the root body. And then each time the policy value network will trying to decide what relation pair it want to choose. And then once it decides the relational pair to choose, it will looking up the dynamic root memory model. And then this dynamic root memory model can be regarded as a lookup table. And then the key in this lookup table is like the relational pair, which is the root body. And then the value of this lookup table is the root head. And then by looking up this dynamic root memory, we know that this selected relation pair can be replaced by this root head. So next we will substitute the relational pair with the root head among all the sample path. So the example is that, for example, the policy value network designed to choose R1 and R2 as the action. And then by searching over the dynamic root memory model, we know that the corresponding root head is R3. So we will replace all the sample root path. We will replace R1 and the relational pair R1, R2 in all sampled root path. In all sampled path by replacing the relational pair with R3 in order to make this long route be shorter. And then by recurrently applying the different action to a path between the query node, the long path will be transferred into a single relation at the end of an episode. So that is like the basic idea of this reasoning as sequence decision making. And then after we introduce like the process of this decision making and the action space, next we will introduce what is the state. Because as we just introduced before, this policy value network will take the state as the input and output the action probability distribution. And then
So I have a question here.
Yes.
So in the previous slide, you say that according to, well, maybe not previous, I don't know which slide. So it's like R1, R2 actually goes to R3.
Right.
And then you're going to replace whenever you see R1, R2 with R3.
Yes.
So in this case, what if like, do they just pick the most likely R3? What if like there are different possibilities? Like, do they choose like top K, or they just pick the most likely R3 here?
They will. So for this like lookup table, for R1 and R2, there's only one possible root head. So if like the decision maker make the decision that now the action space will be R1 and R2, then we will look up the dynamic rule memory model. And then this dynamic rule memory model will return only one rule, will return only one rule head, which is R3.
Do you think it will cause some issue?
Yes.
Okay.
Definitely, because in reality, the rule body could corresponding to multiple rule head,
Mm-hmm.
not only one rule head. Yes.
Mm-hmm. Yeah, so in other words, there could be multi-mode, right? Like if you look at the distribution, R1,
Yes.
R2 could have like multiple peak distribution.
Yes.
Yeah. Okay, great.
Okay. So the next part is that we would like to introduce like the how to build the state of this policy value network. So the representation of so the state will be represented as the representation of all possible relations pair among the current paths. So it will become m plus m multiply m plus n multiply k matrix. So here n is the number of observed relations, and the m is the number of unknown relations, and the k is the dimensional of features of relational pairs. So let me like introduce why we have like the observed relation and the unknown relations here. So the idea here is that we given a relational pair, we trying to replace this relational pair with another head relation, but essentially this head relation could be unobserved in the current knowledge graph. So in order to solve this kind of scenario, this paper will introduce some additional unknown relation in order to represent this scenario. And then therefore the whole relational space for the knowledge graph will be so the total number of relation in this knowledge graph will become m plus n. And then the pair of combination of relation will become m plus n multiply m plus n. And then for each different relational pair, it will associate with a k-dimensional feature in order to represent them. So so finally, the state will be represented as such matrix. And then in order to construct the feature of the relational pair, the author of this paper leverage two levels of information. The first level is statistical feature of the pair. So for example, they will trying to look up the sample path we just introduced here, and then it will trying to calculate the number of co-occurrence of the pair in order to construct the feature of relational pair. And then that is like the statistical feature of the pair. And then another kind of feature is rule related feature. So given the relational pair, it will trying to use the score of the corresponding rule if the pair is in the rule memory to construct such kind of feature, or it will also use indicate whether this relational pair has already been obtained, has been already stored in the rule memory to construct this rule-related feature. So so by doing this, these states just like aggregate all the information related to the relational pair of the sample paths. And then with the action space and the state, the next question is like, now we would like to calculate the reward of the decisions. So the idea here is that during an episode, the actions are applied to a relation path recurrently until the path is deducted to a single relation R. And then after that, the reward will be assigned to all the states in this episode. And then if the single relation R is a no relation, but it is not the target relation, then the reward will be -1. If R is an unknown relation, then the reward will be 0. If R is the target relation, then the reward will be 1. So the idea here is to optimize the decision making in order to make sure by recursively apply the action, we can finally achieve the target relation.
So what does the unknown relation mean?
Unknown relation is just like because we're trying to always replace a rule body with a rule head, but this rule head may not always appear in the knowledge graph. So in order to better represent this rule head, we will randomly initialize n unknown relations in order to represent those kind of rule head.
It's like assign n new IDs to the relation.
Yes.
Like they are placeholder, right? So how can we get information for them?
That is a good question.
Like for example, in your RNNLogic, you just utilize one unknown relation, and
Yes.
they utilize n. How do it?
Actually, in RNNLogic, we are not using one unknown relation. We're just trying to learn the representation of the relation. In that way, there's no need for us to, for example, represent the unknown relation, because unknown relation already has its own representation. Is my expression clear?
Are you saying that in their case, they didn't represent each relation, so they just utilize ID?
Yes.
But in our logic, actually we can represent relation.
Yeah. Yes. So in their framework, they do not, they didn't try to learn a representation to represent each relational pair. Instead, they just like first saying that, okay, we have a space which contained all possible relational pair, which is here. And then for each relational pair, it just trying to create their own features based on the sample path.
And so I'm confused, like if this relation is unknown, how we can collect features, k-dimensional features for that?
I think you just raised a very good question. I also confused about how can they build a feature for this unknown relation.
Maybe it's just like a default, some sort of value they mention in appendix or somewhere.
Oh, I see how they conduct this. Let me just use this as an example. So for example, we begin with path 1, and then assume that R1 and R2 according to the dynamic memory module, R1 and R2 will lead to unknown relation. And then this unknown relation will be used. So we will have an ID for this unknown relation. And then by replacing R1 and R2 with this ID of the unknown relation among all these sample paths, we will achieve a different sample of path. And then based on this sample of path, we will update the feature of the relational pair. Then in that state, the unknown relation will also have like is related to the feature.
Whenever they say, like, for example, R1, R2, and the following relation, they just replace that R1, R2 with that unknown. And
yes.
They utilize that to collect the statistics.
Right.
Then how do they know that it's R1, R2 should correspond to an unknown relation instead of some existing relation?
They just trying to learn it.
So the N is the
the final goal is that okay, I have no idea why in this step I just trying to replace I choose this action and then this action. So first of all, I just want to clarify one thing. So the algorithm here just separates two things. The first thing is that we trying to select a pair of relation as the action, and then that decision is made by the policy value network. And then at this point, we only know that the pair of R1 and R2 are chosen. And then after that, we will have a separate model, which is the dynamic memory model. And then by looking up this dynamic memory model, it is just like a table. And then the root body will be taken as the key of this table. And then the root head will be taken as the value of this table. And then according to this table, it will decide which relation can be used to replace this relational pair. And then so these two things are separate. And then for those like sequential decision making, we only care like the order of the relational pair we're trying to choose. And then we're just trying to replace them. And then after like choosing these things in different order, finally, we can get the target relation. And then this target relation should be the same, should be as the same as the target relation.
So N is a hyperparameter here.
Yes, the N number is the hyperparameter.
Okay.
And then that is like the sequential decision making. And then after that, the model will also have like another component, which is the dynamic root memory. And then we just like mentioned before, this is just a table, and then it will take the relational pair as the key, and it will take the head relation as the head. And then it will trying to use to memorize the candidate rule of length of 2. And then in addition, it will also have like another hash table. And then this hash table will check the rule scores. So by combining these 2 hash tables, we will obtain the complete rule. So for example, given the RB0 and RB1, we can infer RH, and then the confidence score will be the score here. So that is like the dynamic rule memory model. And then this model will also have like a buffer to store the n intermediate unknown relation. So the idea here is that when an unknown relational type is used to complete a rule, it will be removed from the buffer. And then if it is like freed from the rule memory model, it will be added back to the unknown buffer. The idea here is that at each time step, when return an action body AB, it will first trying to look up this dynamic rule memory model. And then if this dynamic rule memory model has already stored the head relation, then then it will return the head relation. If like this action body didn't appear in this dynamic rule memory model, then it will random sample unknown relation to represent the head relation. And then we will update the memory hash table and the computer score by using the following formulas. So the idea here is that if like all relations are null, then they will have like a relatively high score. And then if like the unknown relation in the head, if we have unknown relation in the head and at least an unknown relation in the body, then in this case, this rule will have the most negative score. And then for this 5 case, only the first 2 cases have positive score, and the rest will be regarded as like the negative case. And then this V0, V1, V2, V3, V4 are the cons defined by ourselves. And then during the learning, it will also decay the score of all rule over the episode by using the following formulas. So the idea so if like the score of the rule is negative, then it will become more negative. If the score of the rule is positive, then its value will be become smaller. So the reason is that we would like to so if like a rule is not accessed over the training episode, then we will try to decrease its importance. And then during the training, if a rule score is less than a negative threshold, then we will just eliminate this rule from the rule memory. And that is like the design of the dynamic rule memory model. And then after that, the order just like apply this method to the cluster dataset, and then this dataset is again describe the family relation. And then the idea here is that it will trying to train a graph with 2 or 3 hop edge, and then it will ask to predict the entity, which will have like 4 to 10 hop. So the result is present over here, and then we can see that the proposed method R5 is outperform most of the baseline method in most of the case, which is good. And then it also like trying to provide some population study to investigate the performance of the policy value network. And then the idea here is that it's trying to, without the training this network with the policy value network, and then ask only the NCTS to make the decision, and then the action distribution will given by the number of visits at all possible nodes. And then at this case, we can see that the performance drop quickly. So which means that this policy value network is important in order to make sure that we eliminate the relation in the correct order. That is all about our today's presentation. Any question?
Just curious, is the second work comparing to the first work?
No.
Okay.
Yeah, it only compared to the only baseline method they use to compare with, which is also trying to learn rule, is the CTP.
Okay, got you. Thank you.
Yeah. I think that's all. Thank you for attending the reading group.
Okay, thank you.